All right, so this is the Module 2 project. It is the ternary, the two-digit ternary adder. And so we'll start out by looking at my ternary truth table. So here Cn is equal to 0, and then here Cn is equal to 1. Feel free to pause at any time. And then I converted that into binary and got this. Again, feel free to pause. So this is just the outputs S, G, and P and C out, and they're dependent on Cn, X, and Y. And this is for one full adder. So next, we'll look at the SOP expressions for S1 and S0 and G and P. So I'll start by looking at how I found G and P. So in order to do that, G and P are defined by the C out, the equation for C out. So I made a Carnot map for C out. It's a 5-variable Carnot map. It's dependent on x1, x0, y1, y0, and cn. And then here's the equivalent expression. And if you factor out cn in these last three terms, you get a similar layout to the binary full adder expression where we derive G and P from. So these first three terms are the ternary adder equivalent of G, and this term in parentheses is the ternary equivalent of the propagate. So that's how I got those. And then I had a similar process for S0 and S1. So I made the 5-variable Carnot map and then derived my expression from that. And then S1 Carnot map and the S1 expression. It's here. So that's those. And then my expressions for C1 and C2 are just below that. So C1 is essentially just the expression for C out that I derived earlier. And it's exactly the same here. And then here's it with replaced with G naught and P naught for those expressions. And then C2 is essentially the same expression with x2, y2, y3, and x3, and with Cn being what was C1 in this time. So I replaced what would have been C1 with the expression for it and showed that here. And then I also showed the expression in terms of G1 and P1, and then G1, P1, G0, P0, and Cn. And then this is that same thing with P1 distributed through. So next, in order to determine the worst case gate delay for the carry look ahead and ripple carry adders, I just use the equations that I just showed. So we'll start with the ripple carry adder. So the ripple carry, it'll just go from one adder to the next. So the C out in the first one will be the C out in the next one. So if we start here with the original, and we'll say this is the first step. So the most amount of gates we do is 1 for this first and inside the propagate, and then the whole rest of the propagate is 2, ANDed with CN is 3, and then the ANDed ORed with G is 4. So that's the first step. And after that, the most that carry would be sent to the sum, and that gets, so we'll call that, or to the next sum, so that would be Cn. So I'll use the equation for S0 here for an example. So Cn ANDed would get us 1, and then ORed would get us 2. And that would be the same for any of the Cn's within this expression. And then that would continue to be used throughout the equation, or throughout the ripple carry adder. And so you'd get 2 extra every time. So so we can determine that the worst case gate delay for a ripple carry adder is 2n plus 4 for an n-bit n-digit carry, ripple carry adder in ternary. For the carry look ahead though, all the carries are processed simultaneously, so the most that we get is, actually, sorry, the last one I showed you was the carry look ahead. So that gets us 6, because that's the most that would ever occur. The ripple carry, however, is just 2n plus 4. So yeah, and so I made a table here just showing how what the value of n is, and you can see that it starts out for 4 for both, and then 6 in the next step for both. But then the carry look ahead stays at 6, while the ripple carry just increases by 2 every time. So now we'll look at my implementation of the ternary carry look ahead adder. So here's my code, and feel free to pause at any time. And I attempted to use the hex display, so that's what this is here. I'll let you look at this code here above. Okay, so that's what these are doing. So I just made 3 vectored equation or variables, and then made equations for each of the ternary, or for the hex displays. And then that was the end of the code. So, however, I was not able to get it to work properly. So these first 3 hex displays should be displaying the first digit of ternary, the second digit of ternary, and then the carry, which would be the 3rd digit of ternary. And then the way I have the switches laid out is these first 4 are x values, so x0 to 3, and then y's are up here, so y0, 1, 2, 3, and then my carry in is, so my initial carry C0 is this much. And then the outputs, the other outputs I have were here and here. So these first 2 were the propagate 0 and the generate 0. And then if you go over to the 3rd and 4th, these are the propagate 1 and generate 1. And then this one that's closest to the hex display was my carry 1. So, and the carry 2 was on the hex display. So I managed to get the LEDs to work properly, so you'll notice that I can get a propagate by activating X0 and Y0, or a propagate from activating either Y1 or X1 or Y1, or I can make a generate from X1 and Y1, or sorry, X0 and Y1, and that gets a generate, a propagate, and a carry, and so on. So that all works, but as you can see, my hex display is not working, unfortunately. So that is my ternary carry look ahead adder. Thank you for watching, and have a good night.